work through this examples for the exam here again, just to turn you on to some of the software and perhaps share it out with some others as I ease my way out here into the unknown world of where the gray is a little bit more normal. Alright, so here I'm looking in Smooth Draw, and we're going to now file, and we're going to go to here, and you're not looking, can't see what I'm doing, but I'm going off and I'm adding a layer right now. Add a new layer, and then in that new layer I'm going to import a layer image, and that layer image I had gone out and I had saved and pulled a bunch of these things off, and I'm going to go to the first one to start. See some of my friends there. Okay, and so now you see what the basic problem is. Now with that I can go ahead and now add a new layer, and now in this new layer I can then go back and start doing some colors, and I'll try to just deal with black right now. My black there, and I am now going to be at this point of using my pen. So here, the first one, a black of 10 kilograms is inclined on a ramp. I'm going to go ahead and off on the side here, I'm going to show you got a ramp, right? It's up at 20 degrees, but what you should be thinking is first is what that ramp is if it was flat. And if it was flat, right, you have the free body diagram, that's weight. Remember that double hatch W, and then you've got the normal force backing up N. Now what you would realize is that if it's 0, the cosine of 0 is 1, so it's going to be the cosine is the normal force, and the friction force, which is normal to the normal, will be the sine. So if you remember, it would be the normal force, the force normal, equals M, which is 10 kilograms, times G, which is 9.8, times the cosine of 20 degrees. And the friction force is going to be 10 times 9.8 times the sine of 20 degrees. Now I don't have my calculator, I'm not going to calculate those numbers, but let's look at what that looks like in terms of a free body diagram. Here is your thing. You have the weight down, W, the normal force this way, and the friction force at 90 degrees. Remember, you pick a direction home, dot, dot, dot. You walk out here, this is your weight, and then you pick a direction home. This is your normal force, and then this becomes your friction force. But in class, I kind of talked over and over again about the fact that you've got to be able to do some of these by rote. So I'm going to do a bunch of edits, undos here, edits, undo, edit, undo, edit, undo, edit, undo. And even I can go here, I can turn that layer off if I want, and turn that layer off, and I can go and see if I can do the grab thing. Edit, cut, grab, edit, cut, and even here, I'm going to grab that, edit, cut, turn this back on, and see if I can go here, edit, paste. So that's basically going to pull that over here, and that was my kind of first solution. All right, second one, and we'll work that out in this area down below here. A mass of 10 slugs. Edit, paste. All right. Edit, cut. Now I'm getting a little bit lost. All right, so we're going to go back to here. Pen. 10 slugs. 10 slugs weighs mass times G. Mass is 10 times 32.2. It weighs 322 pounds, or 0.3322 kips. How does that look? It's here, it has one angle, and you have to really think about this. It's rising up with an angle 30 degrees, and the other one is rising up with an angle 45 degrees, which means this has an angle of 30, and this has an angle of, what, 90 plus 45 of 135, and then you have the weight down here, double hatch, the weight of 322. Again, you can do that just by sliding vectors, but I really was trying to, I'm going to work this down here in the bottom here. I was trying to get you to realize you can do it this way. We'll call this tension 1 and this tension 2. And so what you put here is the cosine of 30 degrees, which is in fact, the cosine is the x. Remember all that? Square root of 3 over 2. The sine of 30 degrees, which is 1/2. You put that there. The second one, you put the cosine of, which is going to be the square root of 2 over 2, but it is negative because the x is negative. And then the sine is positive, the square root of 2 over 2. And here, of course, you put the tension 1 and the tension 2. And over here, you put the opposite of the knowns. So the opposite of the knowns is a positive 322. You multiply both sides by the inverse of that, and you get your solution. What is this if you look at it in terms of decimal? I'll wash it out here on the side. 0.866 and then 0.5 and then minus 0.707 and then 0.707. The inverse of that times those two and gets your solution. So that is the process underneath, and we'll kind of post the solutions later. I'm going to once again learn to turn that off. I'm going to grab some of these. All right, turn this back on, I guess. I'm going to do edit, copy, and I'm going to go ahead and edit, cut, and I'm going to move that over here. If I would, put it down here, edit, paste, move that around here. So that's problem number 2, and now I'm going to finally work this last problem on this space that we have here. Edit, paste, I guess. Edit, clear. All right, so, ooh, nice. Edit, paste. So we're really looking to kind of figure out how we clear that, how we clear our pen on this. Edit, deselect all. Okay, so now I'm back to here, I think. All right, back to there. Okay, algebraically with some trig, calculate the swipe direction through the origin. Let me get rid of all this here. Sorry, we're going to go back to here. You can erase all of this. Edit, cut. Okay, back to here. Squiggles. All right. So you remember this one here was a matrix problem, and you did it by the directions of the unit vectors times tension 1, tension 2 equals the opposite of the knowns. You're going to see catching that and then going back to this fact that you're doing the sum of the forces in the x, sum of the forces in the y, and the sum of the forces in the z is an important leap to make here, to not make this stuff more complicated than it is when you got a basic calculator and you know how to use matrices for many different things. You won't find it in the book this way. Again, a lot of these are technical college books, quote unquote, and they ignore the fact that you've got all these other potential support mechanisms in Wolfram Alpha, Mathematica, and even TI-83 calculators. All right. Okay, a force applied at coordinates, okay, 5, 10, 1, 2, 3, 4, 5, and then 10 is someplace up here, with a degree of 30 degrees, all right? So my question is, what in fact is the swipe distance so I can go through the origin? And of course, you know how to do this in CAD, offset through, etc. And how are we going to do this? First off, we have to know what the tangent of 30 degrees is, and it's of course the sine over the cosine. It's 1 over the square root of 3, and we have to know that the cosine of 30 degrees is in fact the square root of 3 over 2. You now go through and you know that y equals mx plus b, or m equals y minus y1 over x minus x1. The slope m, we know, is the same as the tangent of 30, or 1 over the square root of 3 equals y minus y1, which is the y we know, y minus 10 over x minus 5. Multiply both sides by the square root of 3 and divide, and then both sides by x minus 5, and you get x minus 5 equals the square root of 3 times y minus 10. You want this to get this in the form of y equals mx plus b, and so you've got to do a little manipulation, if you would. And you're going to do is, you want it to be y equals mx plus b, so you're going to go and solve this by algebra, which was the whole point. Get your slope-intercept and then multiply by the cosine. So the slope-intercept here is what we're looking for, but we'll put it in the y equals mx plus b. So what do you have? You have x minus 5 equals the square root of 3 times y minus 10 times the square root of 3. All right, we can do a little bit better job. We won't necessarily in this point in time. So we have, bring the other square root of 3 times y equals 5 minus 10 the square root of 3 minus x. Y equals minus x over the square root of 3 minus 10. And now what we're going to do is we're going to take this 10 and multiply by the cosine, which would be the square root of 3 over 2. And that, of course, is our swipe distance. Steps, if you would, and again, I'm kind of looking at getting through here to show you some of the method, so you can rework it again. What were the steps? 1, realize you wanted to write this in, you wanted to do point slope. 2, slope intercept. And 3, multiply the slope intercept by the cosine of the angle. And that will get you the swipe distance. You also, in the end, you could have realized you could have done r cross f with assuming the magnitude of the vector is 1 and gone from there. So what I got here is a swipe distance of 10 times the square root of 3 over 2, which is basically 5 times the square root of 3 for that offset distance. Now, I'm going to check that, but for now, that's the first 3 problems, and I'll grade it out accordingly.